Okay, so on question 25, so I've moved on to the concept of energy here, work and energy. So you've got a block that's held against a spring on a horizontal. This is needs to be rephrased. It's held against a spring with a spring constant, and just ignore this piece. It's meant to probably say on a horizontal surface, but it's held against a spring with a spring constant of 150 Newton meters. The distance d1 is 5 centimeters. We'll assume that this the surface is frictionless, so I'll update this on the printed slides. The hand is then released. How much work is done on the block as it moves from x equals 4 centimeters to x equals 2 centimeters? So, challenging question here, and it can be a little confusing in how the question is phrased, because we're asked by how much work is done on the block as it moves from x equals 0 to x equals 2. So typically, just because it's a block alone, the work net external on a block is typically the delta k of the block. Well, it is the delta k of the block, because the block can only have one form of energy. Assume there's no, if you're just assuming, certainly for frictional surface, it gets a little more complicated when you have a rough surface. So we don't have the mass of the block, and we don't have the change in the speeds of the block, so this is sort of a bit of a dead end. So this is where you have to ask yourself, what's doing work on the block? So the work net external on the block is equal to the delta k of the block, but it's also equal to the work, right here, done on block by spring. So that's the only force that's doing work on the block. So zoom in here. You see this. The work that's done on the block by the spring is only work that's done on the block, because the normal force and the weight force don't do any work. So this is equal to the work done by the spring, which is negative delta U spring. So that's always a true statement. Let's zoom back out here. That's sort of the key to the question. So the work net external on the block is equal to negative delta U spring. So it's negative 1/2 k xf minus xi t squared. Now these x's that are in this equation refer to the distance to which the spring is stretched or compressed from its equilibrium length. That's sort of a difficult and important sort of distinction, that this xf and xi are referring to distances from the equilibrium length of the spring. So the final position or length of the spring is going to be 2 centimeters from it, because again 0 here represents equilibrium length. The initial would have been 4. So the work net external on the block is negative 1/2 150 Newton per meter times 0.02 meters all to be squared minus 0.04 meters all to be squared. So this number will of course be negative. We're taking a small number and doing this right. Double check. Okay, so yes, so this number will be negative times this negative, so we expect the work done on the block to be positive. The block is being pushed to the left by the spring, the block is moving to the left, its displacement is to the left, so both the force and the displacement in the same direction, so the work should be positive, and the block course should speed up. So from between these two, from when it moves from x equals 4 to x equals 2, you should end up with 0.09 as the correct answer. Now I want to address a couple, so that's sort of how you would solve the problem, but there's a couple of extra things we can do with this question just for additional learning. And what's important, or possible mistakes that could be made here. One would be to think that you have the displacement of the block as 0.02 meters, so 2 centimeters, and then multiply that by a force. What you have to realize here is that the force that's exerted on the block is not constant. So you can't just do simply F delta X, because the F is not a constant force over this displacement. So you could draw, and sort of to diagram what we're doing here, we could draw a force position curve for the block. So if we think of plotting maybe the magnitude of the force versus the position, so because the forces would be negative, if I just think about the magnitude of the force, the magnitude of the force is given as K delta L, where this L, delta L represents the displacement from the equilibrium length of the spring. So if you do this for 150 Newton meters and at 5 centimeters, there would be a maximum of 7.5 newtons. Maybe I'll try to see if I can get in 1, 2, 3, 4, 5. So the force position curve would look something like this for the magnitude of the force. Again, the forces would be technically negative. And this has a max value of 7.5 newtons when it's stretched 5 centimeters. But really what we want to figure out, this is the force that's on the block by the spring, the magnitude of the force that's on the block by the spring. Maybe I should zoom in here so you can see this in the extra detail. If we want to find the work done by that force, what we're trying to do is find the area under the curve. And the area under the force position curve is the work done, but we're only trying to find the work done between 4 and 2. So again, this is why you cannot multiply just a single force by the displacement. You want to find this particular area. So you could find the area of the triangle of the entire 4 and then subtract the area of the small triangle. Or find, of course, you find the area of the trapezoid. But if I want to think about what we sort of, it's similar up here, the forces would be given by K delta L, and then the displacements, so if you think about the force half the base times the height, you will end up with this half K sort of delta L squared formula. So if I want to think about this work done, I could think of it as the work is equal to the area of the very large triangle, so 1/2 K times 0.04, so that would be half times the height times the base, which would be 0.04, so that's where you would end up with your 0.04 squared, minus your 1/2, minus it, subtract the small triangle, so again the K times 0.02 times 0.02, that's technically what you have up here. So you would end up with the same, of course, the same answer. So that's thinking it in terms of, force and position. Thinking that the force does vary, of course, it varies according to Hooke's law. So it's not a constant force. Or you can think about the transfer of energy between the block, between the transfer of energy between the spring potential energy and the kinetic energy of the block. So I'll zoom back out here. You can do one more sort of different type of analysis if you draw a potential energy curve. So I'll do it in this space here. So the potential energy, I'll just make a color here so we can separate it. So the potential energy of a spring is 1/2 kx squared. So that's since this will end up being a parabolic shape. If we plot the spring potential energy as a function of x, we should end up with a U-shaped parabola. So I'll just draw 1/2 of that. Oops. Again, I'll just mark out my. Now that I've done this, I should sort of update that these over here this is x in centimeters, so you want to convert that as I've done here. So this is easy to draw. So if you want to do everything correct, of course you should have your x-axis in meters to do everything right. So make sure you convert. So this is just for more, again, this for clarity. So I'll make this in the 0.05 maybe in this example to make it a little clearer. And this is spring potential. So if you do 1/2 of kx squared, excuse me, you should end up with about 0.19 joules. So if you do 1/2 times the 150 Newton per meter times the 0.05 squared, and you end up somewhere in here. And you should get like a nice, nicely shaped parabola. This is the potential energy as a function of position. Now what you find if you calculate it for 0.04, the potential energy stored in the spring is 0.12 joules for the 4, and the energy stored at 2, when it's stretched, compressed to, it's 0.03 joules. So if you're looking at it from a spring potential energy example, there's 0.12 joules stored in the spring when it's compressed 4 centimeters. It's 0.03 joules when it's compressed 2 centimeters. So as it's decompressing, as it's sort of going back towards equilibrium, it's going to it's going to transfer this energy, the difference in this energy, to the block, which of course the difference here is 0.09 joules, which is what we have, of course, from all the different examples. And again, you can think about the 1/2 kx squared, the 1/2 k times the 0.04 squared is initially what you have, the energy in the spring. The 1/2 k times 0.02 squared is what you have final. And in each of these 3 analyses, you should end up, of course, with the same answer. Zoom back out and look at the 3 ways that we sort of address the question.